Okay, so today we are going to solve May-June 2022 paper 22 from A levels chemistry. All right, so let's start with question number one. So in the question number one, it says that magnesium has a melting point of 650 degrees centigrade and high electrical conductivity. All right, so magnesium has a high melting point and it can conduct electricity. Explain these properties of magnesium by referring to its structure and bonding. So it is a 2-mark question and we have to explain why it has a high melting point and why it can conduct electricity based on its structure and bonding. All right, so magnesium is a metal. So that means why it has a high melting point, because it has strong metallic bonding. Strong metallic bonding or strong electrostatic attraction between positive ions and free electrons. Okay, you can say strong metallic bonding or strong electrostatic force of attraction between positive ions and free electrons. All right, and why it can conduct electricity? Because it has free electrons or delocalized electrons available. It has delocalized electrons available. So that's why it can conduct electricity. ठीक है जी. So it was a simple question. Now the next part is that when magnesium is heated in air, magnesium oxide is the major product. So when magnesium reacts with air, when it is heated in air, it reacts with the oxygen present in air and we get magnesium oxide. So smaller amount of magnesium nitride are also made, Mg3 and 2. So major product is magnesium oxide, but a small amount of magnesium nitride would also produce when magnesium is heated in air. Calculate the oxidation number for magnesium and for the nitrogen. Oxidation number for magnesium and for the nitrogen species in magnesium nitride to complete table 1.1. Right, so we just have to write the oxidation numbers. Oxidation numbers of magnesium in magnesium nitride and nitrogen in magnesium nitride. So it is very simple question. So Mg3 and 2, and because magnesium belongs to group 2, that means magnesium would have a charge of +2, and to balance this charge, 2 into 3, that would be +6. Now to balance this charge, nitrogen would have a charge of -3. So the charge of magnesium in magnesium nitrate is +2 and the charge of nitrogen is -3. All right, now the next part is identify the type of reaction which takes place between magnesium and nitrogen. Explain your answer. So what type of chemical reaction is this? Magnesium reacts with nitrogen to get magnesium nitride. So if I write a chemical reaction here, you can see that magnesium reacts with nitrogen and we get magnesium nitride, Mg3 and 2. So if we balance this one, so this would be 3 magnesium on the reactant side. So if you notice, there is a change in oxidation numbers. Magnesium on the reactant side has an oxidation number of 0. And on the product side, its oxidation number is +2. Nitrogen on the reactant side is an oxidation number of 0. And on the product side, it is -3. So that means this is a redox reaction. Redox reaction. So the reaction between magnesium and nitrogen to form magnesium nitride. This is a redox reaction, and explain your answer because magnesium is losing electrons and nitrogen is gaining electron. Or you can write the answer in terms of oxidation states as well. So Mg loses electron while nitrogen gains electron. All right, define enthalpy change of formation, enthalpy change of formation. Now this, you just have to write the definition. So enthalpy change of formation is, it is the energy change which occurs, energy change which occurs when 1 mole of a compound formed from its elements. All right, so this would be the enthalpy change of formation in standard conditions. So this is enthalpy change of formation. Now the next part is related to calculations, and this says that when 3.645 grams of magnesium burns in excess nitrogen to form magnesium nitrite, the amount of energy released is 23.05 kilojoules of energy is released. So magnesium reacts with nitrogen. First, write the chemical equation for this reaction. Magnesium reacts with nitrogen, we get magnesium nitride, and we have 3 moles of magnesium on the reactant side. And what they have given us in this question, they have given us the mass of magnesium. So I have 3.645 grams of magnesium, and it reacts with excess nitrogen, and the amount of energy release is, heat energy release is 23.05 kilojoules when 3.645 grams of magnesium reacts with excess nitrogen. Now the question is, calculate the enthalpy change of formation of magnesium nitride. All right, so that would be the energy change which occurs when 1 mole of magnesium nitride is formed. Right, so we have to calculate the enthalpy change of formation delta HF when 1 mole of magnesium nitride is formed. But to find out the enthalpy change of formation, first I have to find out that what amount or what moles of magnesium nitride is forming in, will form from 3.645 grams of magnesium, because they have given us the energy which is released when 3.645 grams of magnesium reacts with excess nitrogen. So first calculate how many moles of magnesium nitride would form from this much grams of magnesium, right? So first convert moles of mass of magnesium into moles. So for that we need molecular mass or molar mass of magnesium, which is 24.3. So moles of magnesium would be 3.645 divided by 24.3. So that would be equal to 3.645 divided by 24.3, that is equals to 0.15. So we have moles of magnesium. Now next we have to convert this moles of magnesium into moles of magnesium nitride by using the molar ratios. So we have 3 moles of magnesium in equation. 3 moles of magnesium gives 1 mole of magnesium nitride. So whatever the moles of magnesium we have, we get 1/3 of magnesium nitride from that much moles of magnesium, because the molar ratio between magnesium and magnesium nitride is 3:1. So from 3 moles of magnesium, we get 1 mole of magnesium nitride. That means from 0.15 moles of magnesium, we get 0.15 divided by 3, and that would be equal to 0.05 moles of magnesium nitride. All right, so this is the moles of magnesium nitride form when this much grams of magnesium will react with excess nitrogen, and the amount of energy that released would be 23.05. Right, so that means when 0.05 moles of magnesium nitride forms, 23.05 kilojoules of energy would be released, right? But we have to find out delta HF, that means amount of energy released when 1 mole of magnesium nitride form. So what if 1 mole of magnesium nitride form? What would be the amount of energy released? So that would be equal to 23.05 divided by 0.05, and because this is energy released, so the answer which we get would be negative, exothermic. So 23.05 divided by 0.05, and that would be equal to 461 or minus 461. All right, now the next question is related to group 2 elements. Alrighty, so let's start reading question number 2. Radium is an element found in group 2 of the periodic table. ठीक है, तो element we have radium. It is a crystalline solid. So first property, it is a crystalline solid at room temperature and conducts electricity. So radium is a metal from group 2. It is a crystalline solid and it can conduct electricity. Now radium chloride has a melting point of 900 degrees centigrade and is soluble in water. So they have given us a compound of radium, that is radium chloride, and it has a high melting point and it is soluble in water. Predict the lattice structure, the three-dimensional arrangement of particles when they are in space. What is the lattice structure? Three-dimensional arrangement of particles. We can simply describe lattice structure as a three-dimensional arrangement of particles. Now here particles are ions. So predict the lattice structure of radium chloride based on the properties described. So what properties they have given us? That it has a melting point of 900 degrees centigrade. That means it has a high melting point and it is soluble in water. So that means, or that suggests, that radium chloride is an ionic compound. Radium chloride is an ionic compound. All right, it has a high melting point, it is soluble in water. So these are properties of an ionic compound. So what would be its lattice structure? It would be a giant ionic lattice. Right, so we have 4 different type of lattice structure: ionic lattice, metallic lattice, simple molecular, and giant molecular lattice. So this one is a giant ionic lattice. Now the next part of the question is, draw a dot and cross diagram to show the arrangement of outer electrons in radium chloride. So in radium chloride, now radium chloride is an ionic compound and it has a radium ion which has a charge of +2 because it belongs to group 2, and it has chloride ions. And you can see that it has 2 chloride ions, so that means we have to draw 1 radium ion and 2 chloride ions. So 1 radium ion and 2 chloride ion. So to draw the structure of radium ion, first we write the symbol and then the valence shell. We are only going to draw the valence shell. Right, so this is the valence shell of radium. Now once it loses 2 electrons, that means there is no electron present in its valence shell. Radium belongs to group 2. That means it has 2 electrons in its valence shell. But once it loses 2 electrons, so now the valence shell is empty. And this would be the ionic structure of radium ion, and it has +2 charge. So this is the structure of radium ion and the structure of chloride ion. Cl belongs to group 7. So that means it would have 7 electrons in the valence shell. 1, 2, 3, 4, 5, 6, 7. And 1 electron it has gained from radium. So we would draw that electron by a dot. And this would have a -1 charge. Right, and we have 2 of these chloride ions. So you can just simply draw 2 of these chloride ions. Alright, so we have 2 chloride ions and both the chloride ions have -1 charge. So this is the dot and cross diagram for the arrangement of outer electrons. Okay, arrangement of outer electrons in radium chloride. Now the next part of the question is related to the chemical reactions of group 2 elements. Solid radium and calcium shows similar reaction. Now you can see the position of radium in group 2. This is radium, the very last element of group 2, and this is calcium. Alright, so radium is the last element of group 2. So solid radium and calcium show similar reaction with water, but the reaction occurs at different rates. They react in a similar manner, but the speed of reaction is different. Separate samples each containing a single piece of solid radium or calcium are added to equal volume of cold water. So we have two different samples, and in both the samples we have equal volume of cold water, and we in one sample we have added radium, and in the other sample we are adding calcium. Each sample contain equal number of moles of solid and the water is in excess. So moles of calcium and moles of radium are same. Construct an equation for the reaction of radium with water. So a metal reacts with cold water. This is the reaction you're studying since O levels. So when a metal reacts with cold water, we get metal hydroxide, and this time we get radium hydroxide plus hydrogen gas. All right, so now let's check the equation for balancing. So we have two hydrogens here and two hydrogens, so this would be 4 moles of hydrogen. So on the reactant side we would write 2 with water, and now this equation is balanced. All right, so this is the chemical equation when radium is added to liquid water. Now the next part of the question is identify which element, radium or calcium, reacts with water at a faster rate. Suggest how the observations of each reaction would differ. So which element, radium or calcium, reacts with water at a faster rate? Now we know this thing that the reactivity of metals increases down the group. Right, metals get more and more reactive as we go down the group because the ability of losing electron increases. So that means radium reacts faster, but this is not the complete answer because they are asking that suggest how the observation of each reaction would differ. So because hydrogen gas is being produced in both the reactions and radium is solid, likewise calcium would also be solid. So in both the beakers solid will disappear, but radium will disappear at a faster rate. So what would we observe? That radium will disappear at a faster rate because it is reacting more quickly. Right, or you can say that more bubbles of hydrogen gas would form, so or more fizzing, right? But I have described it in the in this way that the metal will disappear at a faster rate. Metal, as it reacts with liquid water, it will convert into radium hydroxide and it will disappear. So soon the metal will disappear. So we can say that radium will disappear at a faster rate. Now the next part of the question is suggest why these reactions occur at different rates. Now they are asking us that initially they asked us about the observations, and now they're asking that give the reason why they are reacting at different rates. So because both are metals, calcium and radium, they are both metals, but the tendency of losing electron for radium is higher than that of calcium. So that means this is its ionization energy. So we can say the ionization energy of radium is less than calcium. That means it loses electron easily, and the reason is it has higher, larger atomic radius, more number of shells, larger atomic radius. Its atomic radius is larger. That means the distance between nucleus and valence electron is very large. So that's why it is easier to remove electron. Plus more shielding. So there are more number of shells, inner shells between the radium nucleus and its valence electron. So they cause more shielding, more repulsion to the valence electron, and becomes easier to remove electron from the valence shell of radium as compared to calcium. And that's why radium is more reactive than calcium. All right, so now the next part of the question is, one of the solutions is cloudy when the reaction has finished. At the end of each reaction, universal indicator is added to each reaction mixture. Now you can see that we are getting metal hydroxide, so that means we are getting an alkali or a base. So that's why they are adding universal indicator. Suggest pH values for the solutions in both reactions. Explain your answer. So pH values for both in calcium. When we add calcium in water, we get calcium hydroxide, and when we add radium in water, we get radium hydroxide. Now both are bases, so that means pH would be higher than 7. pH would be higher than 7, and the pH value of the solution of radium would be higher, as it would be a strong alkali. And the reason is the you know this thing that the hydroxides, they get more soluble. Group 2 hydroxides, they get more soluble down the group, right? So we know this thing that calcium hydroxide would be less soluble, and that's why we get this cloudy solution for calcium hydroxide. But radium hydroxide would be almost completely soluble, so it releases more hydroxide ions. As radium hydroxide is more soluble, it releases more hydroxide ions, so it releases it increases the pH of solution. All right, now the last part is a sample of aqueous calcium halide contain either chloride, bromide, or iodide ions. So we have an aqueous calcium halide which contain either chloride ion or bromide ion or iodide ion. Complete table 2.1 to describe a two-step process that could be used to identify the halide ions present. So we just have to complete this table for the test for halide ions. Right, so what is the test for halide ions? First we acidify with dilute nitric acid, and then we add aqueous silver nitrate. Right, aqueous silver nitrate will release Ag plus ions, and Ag plus will react with the halide ion present in the solution to give us silver halide, which are insoluble in water, and we get precipitates. So if we have chloride ion present in the solution, we get silver chloride, which gives white precipitates. If we have bromide ions present in the solution, we get silver bromide, which gives cream precipitates. And if we have iodide ion present in the solution, we get silver iodide, which gives yellow precipitates. But the problem is, it is very hard to identify that whether it is a white PPT or cream PPT. So just to make sure, we have to do a confirmatory step as well, which would be that we add aqueous ammonia. And when we add aqueous ammonia, if the solution contain halides, or if we get silver chloride, if it is silver chloride, on adding ammonia, the PPT of silver chloride will dissolve. PPT dissolve immediately. So if PPT dissolves immediately, that means it is chloride ion. But if PPT does not dissolve on adding dilute, and it only dissolve if we add concentrated ammonia, then it is bromide ion. So PPT dissolve only in concentrated ammonia, that means it is bromide ion. And if PPT does not dissolve, whether you add dilute or concentrated ammonia, does not dissolve, it remains insoluble. Doesn't matter if we have added dilute ammonia or concentrated ammonia. If PPT does not dissolve, that means it is iodide ion. So the PPT of chloride will dissolve immediately. The PPT of bromide will only dissolve in concentrated solution, and the PPT of iodide will not dissolve. Right, so this is the test for halide ions, and this is it for question number 2. Alright, so the next question that we're going to start is related to chemical equilibrium and group 7 chemistry. Right, so the question says that 0.025 moles of hydrogen iodide is added to a closed vessel and left to reach dynamic equilibrium. The total pressure of the vessel is 100 kilopascals. Right, they have given us the reactant that we have hydrogen iodide. The amount of hydrogen iodide is 0.025 mole. Now this is the starting moles when we have started the reaction, and it reaches dynamic equilibrium, and the total pressure of the vessel is, once it reaches equilibrium, the total pressure is 100 kilopascal. And this is the chemical equation, this is the equilibrium which is established between hydrogen iodide and hydrogen and iodine gas. Now the first part of the question is what is meant by dynamic equilibrium. So this is the simple definition, that what is dynamic equilibrium: when rate of forward reaction becomes equal to rate of backward reaction and the concentration of reactants and product gets constant. Alright, so when both the reactions are happening at the same speed, the concentration of reactants and products will get constant, it will not change. So this is the definition, 2-mark definition for dynamic equilibrium. Now the next part says that describe one difference in the initial appearance of the reaction mixture compared to the mixture at equilibrium. Now you can just simply assume that initially we had only hydrogen iodide present in the reaction mixture. But once equilibrium established, now we have hydrogen as well as iodine gas present in the reaction mixture. Now hydrogen iodide is a colorless gas and iodine is purple gas. Right, so that means the color of the reaction mixture will change from colorless to purple. So one difference in the initial appearance, initially it was colorless, of the reaction mixture compared to the mixture at equilibrium, it goes from colorless to purple. Alright, now the next part of the question is write an expression for Kp, equilibrium constant, in terms of partial pressure for the reaction described in equation 1. So Kp is partial pressure of product upon partial pressure of reactant at equilibrium. So the expression of Kp would be partial pressure of hydrogen and iodine. So this would be partial pressure of hydrogen into partial pressure of iodine divided by partial pressure of Hi square, because we have 2 moles of hydrogen iodide. So this would be the expression of Kp for this particular reaction. Now the next part is related to calculation. At equilibrium, the partial pressure of hydrogen iodide is 86.4 kilopascals. Calculate the amount of hydrogen iodide, amount in moles. Calculate the amount of hydrogen iodide present in the mixture at equilibrium. Show your working. Right, now this is a 2-mark question. We have to calculate the moles of hydrogen iodide at equilibrium, and they have given us the partial pressure of hydrogen iodide at equilibrium, and we also have total pressure at equilibrium, which is 100 kilopascals. Now to find out the number of moles of hydrogen iodide at equilibrium, we would use the formula of partial pressure. How to find the partial pressure of any gas if we know the total pressure, and that formula is partial pressure of hydrogen iodide, because we are talking about hydrogen iodide. So partial pressure of hydrogen iodide is equals to number of moles of hydrogen iodide upon total number of moles at equilibrium into total pressure. So this is the formula that we can use to find out the number of moles of hydrogen iodide at equilibrium. Alright, but to solve this question, we have total pressure, we have partial pressure of hydrogen iodide, but we don't know the total number of moles or the moles of hydrogen iodide. This is what we have to find out. So we will solve this question with an assumption, and that assumption would be, let's say if I solve it here, just to explain it to you, that we have this equilibrium established, Hi, we have hydrogen and iodine. Alright, so now at the start, we have how many moles of hydrogen iodide? 0.025. So initially we have 0.025 moles of hydrogen iodide, 0 moles of hydrogen and 0 moles of iodine. And at equilibrium, obviously hydrogen iodide is converting into hydrogen and iodine. So that means moles of hydrogen iodide will decrease. So at equilibrium, we would have less moles of hydrogen iodide as compared to what we have at the start. Alright, so let's just assume that X moles of hydrogen iodide is used up to achieve equilibrium. Right, so to reach equilibrium, X moles of hydrogen iodide is used up. So at equilibrium, what we are left with? We are left with 0.025 minus X, because X moles are used up. So what we are left with at equilibrium, that would be initial moles minus what amount is used up. So initial moles was 0.025 and X moles are being utilized. So at equilibrium, we have 0.025 minus X. I think everyone gets this point. Now, what moles of hydrogen and iodine would we have at equilibrium? If X moles of Hi are being used up, you can see that the molar ratio of hydrogen iodide and iodine is 2:1. Right, so if X moles are being used up, that means at equilibrium we would have X upon 2 moles of hydrogen that would be produced, because the molar ratio of hydrogen iodide and hydrogen is 2:1. So that means whatever the moles of hydrogen iodide being used up, hydrogen would be produced half of that, 2:1. The ratio is of 2:1. Similarly, hydrogen and iodine, they have a ratio of 1:1. So iodine would also be X upon 2. So this is, now we have the moles at equilibrium, right? With the help of a small assumption, now we have find out the moles at equilibrium. So now we just have to find out the value of X, and then we can easily calculate the moles of hydrogen iodide at equilibrium. So the partial pressure of hydrogen iodide is 86.4. So this is 86.4 is equals to moles of hydrogen iodide at equilibrium is 0.025 minus X, and total number of moles would be 0.025 minus X plus X upon 2 plus X upon 2. So this is total number of moles into total pressure is 100 kilopascals. Right, and let's just solve it for X. So minus X plus X upon 2 plus X upon 2, that would be cancelled out, because plus X upon 2 plus X upon 2, that would be equal to X, and minus X plus X, that would be cancelled out. So what we are left with is 86.4 is equal to 0.025 minus X upon 0.025 into 100. So that would be equal to 86.4 into 0.025 upon 100 is equal to 0.025 minus X. So 86.4 into 0.025 divided by 100. So that is 0.0216 is equals to 0.025 minus X. And if we shift 0.025 on the other side, so that would be minus 0.025. We get minus 0.0034. So X would be equal to, minus would be cancelled out, and we get X is equal to 0.0034. So this is the value of X, right? But we want to know the amount of hydrogen iodide. So this is, the X is the amount of hydrogen iodide being used up in reaching the equilibrium, right? So this is the amount of Hi used up. So what we are left with is, initially we had 20, we have 0.025 moles of hydrogen iodide, and the moles of hydrogen iodide that are used up is 0.0034. So what we are left with is 0.025 minus 0.0034, so that would be 0.0216. All right. Okay, so the next part of the question is use equation 1 and the bond energy values in table 3.1 to calculate the change in enthalpy delta H for the thermal decomposition of 1 mole of hydrogen iodide. Show your working. So equation 1 is 2 moles of hydrogen iodide gives H2 plus I2. So this is when 2 moles of hydrogen iodide decompose, and they are asking us the delta H for 1 mole of hydrogen iodide. Right, so you can solve this question by drawing the energy cycle for bond energies, or you can just simply solve it by the formula that delta H, if we have bond energy data, the delta H would be equal to bond energy of reactants minus bond energy of products. Right, so the bond energy of reactants, this is the reactant side. So we have 2 moles of hydrogen iodide, and this is the energy for hydrogen iodide 299. So if we multiply it by 2, so that would be equal to 299 multiplied by 2, and that is 598. So the bond energy of reactants is 598 minus the bond energy of products. So products are hydrogen and iodine. So 436 plus 151. 436 plus 151, that is equals to 587. So bond energy of reactant minus bond energy of product, that would be equal to 598 minus 587, that is equals to 11. But just remember this thing, that this is the bond energy for when 2 moles of hydrogen iodide are decomposed. And they are asking for us, for 1 mole of hydrogen iodide. So to find out the bond energy for 1 mole of hydrogen iodide, for the thermal decomposition of 1 mole of hydrogen iodide, just divide this value by 2. So 11 divided by 2, that would be equal to 5.5 kilojoules per mole. So this is the energy required to decompose 1 mole of hydrogen iodide. And you can do this question by drawing the energy cycle as well, just to grab the concept that 2 moles of hydrogen iodide decomposes to give H2 plus I2. And what is bond energy? The energy required to break 1 mole of a specific type of bond, right? So on the other side, on the third side of this cycle, we would draw the atoms that we get when these bonds will break. So when 2 moles of hydrogen iodide break, we get 2 moles of hydrogen atom and 2 moles of iodine. So this is bond energy of hydrogen iodide multiplied by 2, and this is bond energy of hydrogen plus bond energy of iodine, because when hydrogen molecule breaks, we get 2 hydrogen atoms, and when iodine molecule breaks, we get 2 iodine atoms. And we have to calculate this delta H, so we can just simply add this cycle by head to tail rule, right? So this arrowhead would be added with this tail, so we get delta H plus this energy change would be equal to this energy change, and you will get the same answer by dividing the value with 2, because the delta H which we would get would be for 2 moles of hydrogen iodide, right? So you can solve it either way. Now the next part is, this is related to again equilibrium. Describe the effect of increasing pressure on the value of Kp for the decomposition of hydrogen iodide. So Kp is equilibrium constant, and equilibrium constant is only affected by temperature. So a change in pressure would not affect value of Kp. So we can just simply say that no change, because Kp or Kc, they get only affected by change in temperature. Now the last part of this question is related to group 7 chemistry. HCl is prepared by adding NaCl solid to concentrated sulfuric acid. When we add sodium chloride to sulfuric acid, we get HCl, H2SO4. When reacts with sodium chloride, we get HCl plus sodium sulfate. So this is the chemical reaction they are talking about. So HI is not prepared by adding sodium iodide to concentrated sulfuric acid, because the HI produced also react with concentrated sulfuric acid. Right, now they're saying just like we have prepared HCl from sodium chloride and sulfuric acid, by adding sodium chloride and sulfuric acid we get HCl. We cannot prepare HI in this manner. Instead of taking NaCl, if we take sodium iodide and react it with sulfuric acid, we get HI. But this is not the right way to prepare hydrogen iodide, and the reason is that hydrogen iodide produced also react with concentrated sulfuric acid. The HI which we get from this reaction will react with sulfuric acid, and we cannot get the desired product, because we want to get HI, but that HI which will produce from this reaction will react with H2SO4 and will convert into some other product. So identify the type of reaction that occurs when sodium iodide reacts with concentrated sulfuric acid to form HI. What type of reaction is this? So just like we have written reaction for H2SO4 and sodium chloride, when H2SO4 reacts with sodium iodide, we get HI, hydrogen iodide, plus sodium sulfate. So now what type of reaction is this? In this reaction, sodium is displacing hydrogen from an acid, and so that means it is an acid-base reaction. Whenever a metal replaces hydrogen from an acid, so this is an acid-base reaction. So in this reaction, H2SO4 is acting as an acid, and because it is accepting proton, sodium iodide is accepting proton, so it is a Bronsted base. So this is acting as a base. So this reaction is an acid-base reaction. Write an equation for the reaction of hydrogen iodide with concentrated sulfuric acid. Now that's what they have tell us in this part, that the HI produced from this reaction will react with sulfuric acid. And now they are asking us for the reaction which will occur between sulfuric acid and hydrogen iodide. So when sulfuric acid reacts with HI, now this is a redox reaction. You have studied this reaction in group 17 chemistry. So this is a redox reaction. Iodide will be oxidized into iodine, and sulfur will be reduced into hydrogen sulfide, plus we get water. So this is a redox reaction. Now let's balance this chemical reaction. So we have two hydrogens on this, two iodines, so this would be 2HI. Now to balance, let's find out the oxidation states, just like we balance a redox reaction. So the oxidation state of iodine, let me just balance this equation here, so that you all get clear idea how we are balancing this equation. So H2SO4 reacting with HI to give iodine plus H2S plus H2O. So whenever we balance a redox reaction, first of all, let's just confirm if this is a redox reaction by applying the oxidation states. Iodine is -1 on the reactant side, and on the product side it is 0. So -1 to 0, that means it is losing electron, oxidation state is increasing, so iodine is oxidized. Sulfur on the reactant side, this is -2 into 4 -8, plus 1 into 2 plus 2, so sulfur is +6. And on the product side, this is -2. So sulfur is losing electrons, and how many electrons? 8 electrons, +6 to -2, so that means total 8 electrons lost. Now to balance this equation, first of all we have to balance those elements, we have to balance elements other than hydrogen and oxygen, right? So we have 2 iodines on the product side but only 1 iodine on the reactant, so place 2 with 2 HI and then balance the charge, right? We have total 2 iodines and 2 iodines are being converting into iodine, so that means total loss of electron is of 2 electron. So loss of electron, we have loss and gain of electron is not balanced, right? Total loss of electron is of 8, gain of electron 8 and lost electrons 2. So to balance loss and gain of electron, we will multiply this 2 by 4. So loss and gain will get balanced. So that means we have to multiply Hi and I2 with 4. So when this 2 will be multiplied by 4, so that would become 8. 2 multiplied by 4, that would be 8. And 4 ones are 4, so that would be 4. So now iodine is balanced, charge is balanced. Finally, we have to balance oxygens. We have 4 oxygen on the reactant side, so that means place 4 with H2O. Now hydrogens are also balanced. 4 2s are 8 plus 2 10. 8 plus 2 10. So now this is a balanced equation. So you can just simply write this equation here. Right, so that would be equal to H2SO4 plus 8HI gives 4I2 plus H2S plus 4H2. So this is a balanced reaction between H2SO4 and hydrogen iodide, in which a redox reaction has been happening. Now, last part of this question is explain why hydrogen iodide reacts with concentrated sulfuric acid, whereas HCl does not. HCl does not react with H2SO4, but HI can react with H2SO4. The reason is HI is a stronger reducing agent than HCl, right? So the reason is because in this reaction HI is acting as a reducing agent. It has reduced sulfur from +6 to -2. So that means HI is a stronger reducing agent. HCl cannot reduce H2SO4. So the simple answer is that HI is a stronger reducing agent than HCl. Down the group in group 17, the strength as a reducing agent increases and the strength as an oxidizing agent decreases. So this is the last part of this question. Alright, so this next question is from organic chemistry. Alright, so let's read the question. Bromine reacts with butane in the presence of ultraviolet light to form bromobutane. Alright, so this is a reaction of alkanes reacting with halogen, halogenation of alkanes. Bromine is reacting with butane. Now, the two structural isomers with the molecular formula C4H9Br are produced during this reaction. Draw the two structural isomers and state the systematic name of each isomer. Now, what are structural isomers? Those which have same molecular formula but different structure. So they're saying that we have butane. Now this is butane, 1, 2, 3, 4. Right, so in butane we have 4 carbon atoms, and with each carbon atom there are hydrogens attached. And they're saying that when we react it with bromine, 2 structural isomers will produce. So this is mono substitution reaction because they have given us the molecular formula of the product. This is C4H9Br. So that means one of the hydrogen atom is being displaced, right? And like if we displace hydrogen atoms from butane, how many different C4H9Br can we get? For example, if we replace hydrogen from this first carbon atom, so let's suppose we get a Br on this carbon atom. So that would be 1, 2, 3, 4, 1 bromobutane. And let's suppose if we replace hydrogen from the second carbon, then we get Br on the second carbon atom. And in that case, that would be 2 bromobutane. But if we replace hydrogen from the third carbon atom, then let's suppose from this carbon atom and we get a Br on this carbon atom, then it would not be 3 bromobutane, because then according to the naming rules, naming will start from right hand side, because we have to name the structure from where the carbon containing halogen gets the smallest number, right? So in that case, we would name the structure from the right hand side and it would be 1, 2. So again, it would be 2 bromo. So that means from butane, when we do a mono substitution reaction with butane and we get C4H9Br, we only get 2 structural isomers, and that would be 1 bromobutane and 2 bromobutane. So let's draw the structures of these 2 compounds. So it would be, now they haven't mentioned that we have to draw we have to draw a structural formula or a displayed formula. So let's just draw, or a skeletal formula. So we can just simply draw any kind of formula. So I'm drawing skeletal formulas here. So 1, 2, 3, 4. And if we have a Br on the first carbon atom, so it would be 1-bromobutane. So the name of the compound is 1-bromobutane. And then it can be on the second carbon. So 1, 2, 3, 4. Again, we have 4 carbon atoms, and on second carbon, this time bromine is on the second carbon. So that would be 2-bromobutane. All right, now the next type of question is identify the type of structural isomers shown in A1. So we have studied 3 different types of structural isomers: chain isomers, position isomers, and functional isomers. And because in these 2 isomers, the position of Br group is changing. In the first structural isomer, Br on the first carbon atom, and in the second structural isomer, Br is on the second carbon atom. So that means they are positional isomers or position isomers. So the type of structural isomer is positional isomers. All right, now the next part of the question is, halothane is an anesthetic, and they have given us the structure of halothane, in which the carbon atoms are connected to fluorine, chlorine, bromine, and hydrogen. Identify the chiral center in halothane and mark with an asterisk. Now, what is a chiral center? Which is attached to 4 different groups. Carbon which is attached to 4 different groups. So if we look at this carbon atom, it is attached to a Cl, a hydrogen, a Br, and this 4th group. Right, so this particular carbon is attached to 4 different groups, and that means it is a chiral center. So we can just simply draw a steric on this carbon atom. Right, so this is our chiral carbon. If you look at this carbon atom, it is attached to 1, 2 fluorines, and then 3 fluorines. So that means this is not a chiral center. Right, so this one is the chiral center because it is attached to 4 different groups. Now, when halothane reacts in ultraviolet light, homolytic fission occurs. What is homolytic fission? When bond break and both the atoms take back their electron. There are 2 types of fission: homolytic fission and heterolytic fission. So when, let's suppose if these are 2 atoms, and if homolytic fission occurs, this atom will take back its electron and this will take back its electron, and we get free radicals. Due to homolytic fission, we get free radicals, particles with an unpaired electron. And another type of breaking is when both the electrons are being taken by one particular atom, then we get electrophile and nucleophiles, and this happens due to difference of electronegativity. Right, so these are 2 different type of fission, and they're saying that when halothane reacts in ultraviolet light, homolytic fission occurs and the CBr bond is broken. So they have told us that what bond will break. So construct an equation to show the homolytic fission of halothane CF3CHBrCl. So we have to construct an equation for the homolytic fission of CF3CHBrCl. So they have already told us that the CBr bond will break. That means, let me just erase this all. So that means this particular bond will break and this will break because it is homolytic fission. So that means it will break homolytically. This bromine will take back its electron and this carbon will take back its electron. So that means we get free radicals, and we get a bromine free radical and CF3CHCl. Because Br is lost, so we get 2 free radicals. One is bromine free radical and the other one is this free radical. Both the bond breaks and both the atoms take back their electrons. All right, now the next part of the question is complete figure 4.2 to show the arrangement of electrons in a bromine atom using the electron in box notation. right? So we have to complete the electron configuration of bromine. They have given us the boxes. They have like 3D, 4s and 4p, and they have written the configuration of bromine in terms of noble gas, right? So like let's just check out how many electrons bromine has. So this is bromine and it has 35 electrons, right? But they have written the configuration in terms of argon. So that means first 18 electrons. Argon has 18 electrons. So first 18 electrons would be filled like just filled like argon. So after argon, we moves into the 4s, because this is S block, right? Everyone knows this thing, I hope. Okay, this is our S block, this is D block, this is P block. So if we jump into S block, and which S block is this? This is first, second shell, second period, third period, and fourth period. So we are in fourth period, so that means first we have to fill 4s, right? So 4s, it would have 2 electrons, and then afterwards, after 4s, we jump into D block. This is our D block, and D will always be filled n minus 1. That means if we are in fourth shell or if we are in fourth period, so 3D will be filled. If we are in fifth period, then 4D will be filled. D will always be filled n minus 1. So that means if we have previously we have filled 4s, now 3D will be filled. And 3D would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. So that would be 1, 2, 3, 4, 5. Because all the orbitals which are present in D, they are of same energy level. So when we are filling the orbitals of similar energy level, first we have to fill them singly, and then doubling takes place. So 5 electron, then 6, 7, 8, 9, and 10. So we have filled 10 electrons in D orbitals, and then we move into the P orbital, and P would be filled just like S, like in whatever shell we are. So that means 4p would be filled. And how many electrons are present in 4p? 1, 2, 3, 4, 5. So we have to fill 5 electrons in 4p. So it would be 1, 2, 3, 4, 5. So this would be the electron configuration of bromine. Now we can just simply count the electrons. Argon 18 electrons, then 18, 19, 20. Then D has 10 electrons, so it would be 30. And finally 4p has 5 electrons, so this would be 35 electrons. So bromine has total 35 electrons, and this is the electron configuration of bromine. All right, now the next part of the question is X is an addition polymer. Draw the monomer of X. So the monomers of addition polymers can be very easily drawn. You just have to look at the 2 horizontal carbon atoms. So let's suppose these are the 2 horizontal carbon atoms. Just draw these 2 carbon atoms and look for the groups which are attached to these 2 carbon atoms. So this carbon atom is attached to 2 because we are only seeing 2 bonds of this carbon. 1, 2. That means the other 2 bonds are with hydrogen. So that means it has 2 hydrogens, and this carbon has a hydrogen and CH2 Cl, right? So it would be CH2 Cl, right? And then addition polymers, they are formed from alkenes. So that means these 2 carbon atoms, they have a double bond present between them. So we just simply draw a double bond, and this would be the structure of the monomer. So this is very easy to draw the monomer of addition polymer. Just identify 2 horizontal carbon atoms and look for the groups which are attached to these 2 carbon atoms. Then finally place a double bond between these 2 carbon atoms. Now the last part of this question is suggest one reason why the disposal of items made from X is difficult, right? So X is an addition polymer, and it is difficult to dispose of the items made of X because addition polymers, they are non-biodegradable. Just one word answer, they are non-biodegradable. All right, so this is the end of this question. All right, now the next question is related to halogenoalkanes. And this saying that figure 5.1 shows 3 reactions of 2-bromopropane, right? This is 2-bromopropane, and they have given us 3 reactions: reaction 1, reaction 2, and reaction 3. Complete table 5.1 for each reaction by stating the reagent and conditions used, and identify the type of reaction that occurs, right? So first of all, in reaction 1, if we can see that 2-bromobutane is being converted into butane 2-ol, sorry, propane 2-ol, right? This is carbon number 1, carbon number 2, carbon number 3, and carbon number 2 has an OH group. So instead of Br, now we have an OH group. So that means the type of reaction is substitution. It is a substitution reaction in which Br is being replaced by OH group. And for substitution, the reagent that we use is aqueous sodium hydroxide, in which OH is being used as nucleophile, right? So this is nucleophilic substitution. You can write nucleophilic substitution or simply substitution, and heat under reflux. Right, now the second reaction is we have 2-bromopropane, and instead of Br, we get amine group, right? So Br is being replaced by NH2. So this is aminopropane, 2-aminopropane. So here the substituent is NH2. So again, this is a substitution reaction in which Br is being replaced by NH2. So this is again substitution, and this time the nucleophile would be ammonia. We react bromopropane with ethanolic or alcoholic ammonia. So we would have ethanolic ammonia, and condition would be heat under pressure or heat in a sealed glass tube. Right, so you have to remember the conditions for each reaction. And the final reaction is, because and the last reaction is, we can simply see that 2-bromopropane is being converted into propene, right? So from 2-bromopropane, we get an alkene. So that means it is an elimination reaction. The carbon which is connected to Br, it has lost its Br, and the neighboring carbon atom, both the carbon atoms has 3 hydrogen atoms. So that means any one of them can lose a hydrogen. So this carbon has lost Br, and let's suppose this carbon has lost a hydrogen. So this is an elimination reaction. Elimination reaction, and condition would be, this time we use NaOH alcoholic or NaOH in ethanol. So just remember this thing, that if you use aqueous sodium hydroxide, then substitution occurs, and if we use ethanolic NaOH, then elimination occurs. And again, we have to heat under reflux, right? So these are reagents and conditions, and we have write down the types of reaction as well. Now the next part of the question is, a sample of 2-iodopropane reacts under the same condition as reaction 1 to produce propane 2-ol, right? Just like 2-bromobutane, from 2-bromopropane we get propane 2-ol. Similarly, we can get 2-propanol from 2-iodopropane. So instead of a Br, now we have an iodine group present. Explain why 2-iodopropane reacts at a faster rate than 2-bromopropane. So this is CH3, CH, CH3, and this is 2-bromopropane. This is CH3, CH, CH3, Ci, and this is 2-iodopropane. So why iodopropane reacts at a faster rate than bromopropane? The reason is the bond length of CBr and Ci bond. We can just simply say that carbon-bromine bond would be difficult to break as compared to carbon-iodine bond. You can just simply look at the bond energies from the data booklet. So here the bond energies are mentioned. The bond energy of CBr bond is 280, and the bond energy of Ci bond is 240. So that means Ci bond is easier to break, and the reason is its bond length, because iodine is a larger atom. So the bond between carbon and iodine would have a higher bond length and it would be difficult to break. But the bond between carbon and bromine, that would be of smaller bond length and it would be difficult to break as compared to CBr. So Ci bond would be easier to break due to its larger bond length. So we can just simply say that why 2-iodopropane reacts faster? The reason is Ci bond in 2-iodopropane is weaker, right, due to large atomic radius of iodine. The bond length of Ci would be larger, right? So it would have a larger bond length, so it would be easier to break. So it requires low activation energy. Less amount of energy would be required to initiate the reaction in case of 2-iodopropane, right? Now, the next part of this question is figure 5.2 shows butane 1-ol can be made from 1 bromopropane. So this is 1 bromopropane, right? And this is 1 butanol. So we are getting butane 1-ol from 1 bromopropane in 3 steps. Okay, they have given us 3 steps. Step 1, step 2, step 3. In step 1, 1 bromopropane reacts with a cyanide to form butane nitrile. So that means it is a nucleophilic substitution reaction in which nucleophile is cyanide group. Now what we have to do, figure 5.3 to show, complete figure 5.3 to show the mechanism for step 1. Include charges, dipoles, lone pair of electrons and curly arrows as appropriate. So this is nucleophilic substitution, and because we have primary halogenoalkane, right? What is a primary halogenoalkane? In which the carbon which is attached to bromine has only one carbon directly attached. So this carbon has only one carbon, this carbon directly attached. So that means this is a primary halogenoalkane. So if we have a primary halogenoalkane, we have 2 different mechanisms for nucleophilic substitution. It could be either SN1 or SN2, but because it is a primary halogenoalkane, so the reaction would occur through SN2 mechanism, which is a single step reaction. So both bond breaking and bond making will occur in a single step. So let's write the mechanism, but first erase all this. Now we have to show the mechanism for step 1, include charges. So first of all, we would draw the charges on carbon and bromine. This is partial negative, carbon is partial positive, and cyanide. So this, we have mentioned the charges. Then dipoles, so these are dipoles, partial positive, partial negative, and lone pairs. So this carbon would have a lone pair as well, right? This would have a lone pair and negative charge. They have already shown the negative charge. And finally, we would show the curly arrows. So the nucleophile would attack on partial positive carbon atom, right? So we will draw an arrow from the lone pair of carbon toward this partial positive carbon atom, and when this cyanide ion will transfer its electron density towards this partial positive carbon atom, or when this cyanide ion will try to make a bond with this carbon, these electrons will be transferred to Br as it is more electronegative. It is a good leaving group. So these electrons will be transferred to Br. So this would be the mechanism we have drawn. We have included charges, dipoles, lone pairs of electrons and curly arrows on both sides, right? So that means on one side, cyanide is transferring its electron density towards carbon, and on the other side, Br is moving away, right? Both these bonds, this bond is being broken down heterolytically, and Br will move away as a lone pair. This is Br minus, and finally we get cyanide ion attached to the carbon, right? Now, in the next step, they're saying in step 2, butane nitrile is heated with HCl aqueous. So step 2, this is butane nitrile, carbon number 1, carbon number 2, carbon number 3, carbon number 4. Both carbon and nitrogen have a triple bond between them. So this is butane nitrile, right? And they're saying that it is reacting with aqueous HCl. So that means hydrolysis occurs. And when hydrolysis of nitriles occur, we get a carboxylic acid. So this is carboxylic acid. You just have to remember this reaction. Construct an equation for the reaction in step 2, right? So just to write the equation, first just draw the butane nitrile so that you can get an idea what is happening in the reaction. So this is butane nitrile, CH3, CH2, CH2, CN. And when we reacted with aqueous HCl, right? So that means we have HCl present and in aqueous medium, so water is also present. So this bond between carbon and nitrogen, this is a hydrolysis reaction. So the bond between carbon and nitrogen will break and carbon will be converted into, this carbon will be converted into carboxylic acid. So we get a carboxylic acid. So we will write the equation here. This would be CH3, CH2, CH2, CN reacts with H2O plus HCl. And first of all, the bond between carbon and nitrogen breaks and we get carboxylic acid. The cyanide will be converted into carboxylic acid, COOH, plus this nitrogen would be converted into ammonium ion, and ammonium ion will combine with this chloride ion to form ammonium chloride, right? This will convert it into ammonium chloride. Now finally we have to balance the reaction. So we have 4 plus 1 hydrogens, right? So 1 hydrogen with HCl, so we can write 2H2O. Now we have 2 oxygens on the reactant side and 2 oxygens on the product side. So now this equation is balanced. So this is the hydrolysis of nitriles. Just remember this reaction. Whenever acidic hydrolysis of nitriles occur, we get carboxylic acids and ammonium salt, right? So this is acidic hydrolysis of nitriles. Now the next reaction is step 3 is a reduction reaction. So you can see that this carboxylic acid is being reduced into alcohol, right? So step 3 is a reduction reaction in which we have reduced a carboxylic acid into alcohol. So construct an equation for the reduction reaction in step 3. Use atomic hydrogens to represent one atom of hydrogen from the reducing agent, right? So we have to write the equation for the reduction. First, let's erase this thing. Now, so we have a carboxylic acid, CH3, CH2, CH2, C double bond O, OH, and we reacted with some reducing agent, which we will react through, we will show through this atomic hydrogen, right? And in this reduction reaction, what would happen? You just have to remember that this carbon, which is directly bonded to this, double bonded to this oxygen, this will lost this oxygen and gain 2 hydrogen atoms instead of this oxygen. So we get CH3, CH2, CH2, COOH plus H, and this bond will be broken, carbon and oxygen bond, and this carbon will gain 2 hydrogens. So it becomes CH3, CH2, CH2, and this carbon will gain 2 hydrogens. So this also becomes CH2 and we get OH, right? So OH was already there, but this oxygen will be lost, right? And this oxygen will combine with 2 hydrogens to form H2O. So that means in total 4 hydrogens are being used. 2 of these hydrogens will be attached to the carbon, and 2 of the hydrogens will be attached to oxygen. The double bond which we have here, both these carbon and oxygen will gain 2 hydrogens, right? So this will gain 2 hydrogen, it becomes CH2, and this will gain 2 hydrogen. This bond will break and it will gain 2 hydrogen and becomes water. So that means we have 4 hydrogens present, right? Just remember these equations. This would be the best way to do these questions. If you memorize these reactions, then you can simply, it will save your time as well in the paper, right? So memorize all these reactions. Now, the last part of this question is state the identity of a suitable reducing agent in step 3. So carboxylic acid needs a strong reducing agent, right? A strong reducing agent. And what strong reducing agent do we have in our syllabus? That is lithium tetrahydroaluminate or LiAlH4, lithium tetrahydroaluminate, and the solvent is used is dry ether. Because it is highly reactive, we cannot dissolve it in water, so we use dry ether as a solvent, right? So this is the last part of this question, and now we move on to the last question of this paper. All right, so this is the last question from this paper, and this question states that Z is a molecule which contains the element carbon, hydrogen, and oxygen only. Z contain only alkene and carboxyl functional group. All right, so Z is an alkene. It has two functional groups. It has an alkene and a carboxyl functional group. So that means it has both carbon-carbon double bond and C double bond O, OH group present. And it has three elements, carbon, hydrogen, and oxygen. So complete table 6.1 by describing the observations that occur when two different reagents are added to separate samples of Z. So we have to complete the observations. And first, when we added bromine in Z. Now because Z contains alkene, right? And when we add bromine into an alkene, addition reaction would occur because aqueous bromine is of orange color, so it changes its color from orange to colorless. All right, and the next reaction is when we reacted Z with sodium carbonate. So sodium carbonate will react with acid to give salt, water, and carbon dioxide, right? The signature reaction of acids. So because carbon dioxide gas would produce, so we can say that the observation would be fizzing or effervescence. All right, so very simple questions. Now the next part, they're saying that table 6.2 shows the percentage by mass of each element present in Z. So carbon percentage, hydrogen percentage, and oxygen percentage. Use the data in table 6.2 and demonstrate that the empirical formula of Z is CHO. Show your working. So we have to prove that the empirical formula of Z is CHO. So we have three elements, carbon, hydrogen, and oxygen. First, we will calculate the moles. So we would divide the percentage by mass with the molar mass of these elements. So 41.38 divided by 12, 3.45 divided by 1, and 55.17 divided by 16. So that would be equal to 3.45, and 3.45. So that means all the three values are similar. So if we calculate the simplest ratio, and how we calculate the simplest ratio, by dividing all three moles with the smallest value, but here all the three values are same. So that means the simplest ratio would be 1:1:1, and that means the empirical formula is CHO. This is the empirical formula of compound Z. All right, in the next part, they have given us the mass spectrum of Z. Now, Z is a molecule, and they have given us the mass spectrum of Z. Now, you all know this thing that this is previously this topic, mass spectroscopy of organic compounds. This is basically mass spectroscopy of organic compounds. So this topic is previously was in A2, but last year they move it in AS syllabus, right? So this is the first time when it comes in AS paper 2. So the question says that it shows the mass spectrum of Z, right? We have this mass spectrum of Z. What happens is that Z get ionized and it passes through the mass spectrometer, and due to fragmentation some of the molecular ions will break, and we get these peaks when these molecular ions and the fragments, when they hit the detector, we get these peaks. So we have four peaks present here, a peak at 45 and a peak at 71, a peak at 116 and a peak at 117. Right, now they're asking that reduce the molecular formula of Z. Explain your answer by referring to the molecular ion peak in figure 6.1 and the empirical formula of Z. So we have to deduce the empirical formula, molecular formula of Z. Okay, by referring to the molecular ion peak. Now, what is a molecular ion peak? A molecular ion peak is the peak at the extreme right of the graph, right? The most significant peak on the extreme right. So molecular ion peak is the most prominent peak on extreme right. So we know that the peak at 116, this would be the molecular ion peak, and it might comes in your mind that why not 117? But these two peaks, like the peak at 116, this is the most prominent peak, so we would call it M plus peak. This is the molecular ion peak, and the peak just after that, that is the peak at 117. This is M plus 1 peak. Right, if you have studied the topic, this is M plus 1 peak, and this is due to carbon 13. All right, so we have to find out the molecular formula. So the M plus peak is at 116. So that means this is the molecular mass of Z. Now we have the molecular mass of Z, and next we have to find out the ratio between the molecular mass and the empirical mass. So the ratio between molecular mass and the empirical mass. We have already calculated the empirical formula in the last part. So empirical mass. Now this we are doing to find out that what is the ratio between molecular mass and empirical mass, or molecular mass is how many times of the empirical mass. So molecular mass is 116 and empirical formulas was CHO. So this is 12 plus 1 plus 16. So that would be equal to 29. 116 upon 29, that would be equal to 4. So we can just simply say that the molecular formula is 4 times of the empirical formula. Molecular formula is 4 times of empirical formula. So that means the empirical formula is C4H4O4. We have multiplied the empirical formula with 4. So this would be the molecular formula of compound Z. Now in the next part they're saying, use figure 6.1 to suggest the formula of the fragments with the mass to charge peak at 45 and 71. The peaks at 45 and 71, what fragments are responsible for these peaks? Because we know this thing that when a molecular ion moves through a mass spectrometer, let's suppose if this is a mass spectrometer, right? So when a molecular ion moves in this mass spectrometer, what happens is that sometimes they collide with each other, or they collide with the high-speed electrons, due to which this molecular ion will break into further fragments, right? It breaks into fragments, and then these fragments will hit the detector. So let's just suppose that if we have entered 10 molecules of the 10 particles of the molecule Z in the mass spectrometer, and out of those 10 molecules, let's say 7 gets ionized, right? So we have 7 M plus particles, and out of those 7 M plus particles, 3 or 4 get further fragmented, and the rest will hit the detector as a molecular ion, right? So let's suppose 3 molecules will hit as a molecular ion, and the other 4 will be break into fragments. So they are asking us that what fragment is responsible for the peak at 45. So you just have to count the carbon, oxygen, and hydrogen for the peak at 45. Like let's suppose if we have 1 carbon and 2 oxygen and a hydrogen, because we know this thing that we have carboxylic acid present in our molecule. So let's start with the simplest one. So if we add these 3, carbon plus 16 into 2 plus 1, so that would be equal to 45. So we can just simply say that the fragment responsible for the peak at 45 is COOH, right? And the next one is 71. Now the total mass of the compound is 116, and one of the fragment was at 45. So let's suppose if we subtract 116 from 45, if we subtract 45 from 116, we get 71, right? So this is the peak at 71. What could it be? The actual formula is C4H4O4, and you've said that the peak at 45 was due to CO2H. So if we subtract two oxygens from C4H4O4, that would be O2, a hydrogen, so that would be H3. We would be left with 3 hydrogens, and we are left with 3 carbons. So this would be the fragment responsible for the peak at 71. If you add their atomic masses, it would be 12 into 3 plus 3 plus 16 into 2, that would be equal to 71. So the fragment responsible for the peak at 71, that would be C3H3O2 plus. Now the last part of the question is suggest the structure of Z using the relevant information from table 6.1b and c. Now we have to find out the structure of Z. Now we know this thing that the molecular formula of Z is C4H4O4, C4H4O4. The next thing we know is that it has an alkene and it has carboxylic acid, because in the first part it has been confirmed for alkene and carboxylic acid by reacting it with bromine and sodium carbonate. So that means it contains both alkene and carboxylic acids, and as it has 4 oxygens, right, and a carboxylic acid functional group has 2 oxygens present in it, so that means it is a dioic acid. It has 2 COOH, 2 carboxyl group present. So if I start with the structure, let's suppose this is C double bond OH, then next carbon, and because there is a double bond between carbon, so let's place the double bond between these 2 carbon atoms, and now we are only left with 1 carbon and 2 oxygen and a hydrogen, right? So this carbon has a hydrogen and this carbon has a hydrogen. So if we now count the atoms, so we have 1 2 3 4 carbons, 1 2 3 4 4 oxygens, and 1 2 3 4 4 hydrogens, right? So, and because it has a carbon-carbon double bond, that means it would decolorize bromine, and if it has this carboxyl group, that means it will give fizzing when reacted with sodium carbonate. So this would be the structure of molecule Z.